two ancient travelers, one impossible year. A cosmic mystery that has astronomers questioning everything. If you thought 2025 was just another year, think again. Within months of each other, two of the most extraordinary objects ever detected arrived in our solar system. And the timing might not be a coincidence. 3I Atlas, a massive interstellar comet from another star system, carrying secrets from the deep space between stars, moving at 60 kilometers per second with anomalies so strange that Harvard scientists are asking, could it be artificial? SWAN R2, a 22,000-year wanderer from the edge of our own solar system, hidden behind the sun for months, emerging with a tail 5 times the width of the full moon. What are the odds? What does their timing mean? And what if they had collided in the darkness billions of miles away? Tonight, as you drift into sleep, let's explore the greatest cosmic mystery of our time. Subscribe now to join millions discovering the universe's deepest secrets. Somewhere in the vast darkness between stars, two ancient travelers have been making their way toward our small corner of the galaxy for tens of thousands of years. One, a visitor from another star system entirely, carrying secrets from a place we'll never see. The other, a wanderer from the very edge of our own solar system, returning home after a journey that began when our ancestors were still learning to make fire. The year 2025 would become known in astronomical circles as the year of cosmic visitors. It began quietly enough, with astronomers going about their routine surveys of the night sky, cameras and telescopes scanning the heavens for anything unusual. Little did they know that by year's end, they would have documented not one, but two of the most significant celestial discoveries in human history. The first visitor announced itself on July the 1st, when the Atlas Survey Telescope in Chile detected something moving far too fast to belong to our solar system. The object, which would soon be designated 3I Atlas, was traveling at approximately 60 kilometers per second, twice the speed of anything humans have ever built. This wasn't just unusual. It was impossible for any object gravitationally bound to our sun. The mathematics were clear. This traveler had come from the space between stars, from depths so vast that light itself takes years to cross them. Dr. David Jewett of UCLA, one of the astronomers studying the object, would later remark that 3I Atlas was the fastest thing we've ever seen coming through the solar system. But speed wasn't its only remarkable quality. As telescopes around the world turned their attention to this interstellar visitor, they discovered it was massive, potentially up to 20 kilometers across, dwarfing the previous interstellar objects that had graced our skies. For 2 months, 3I Atlas held the spotlight of the astronomical community. Papers were written, observations were coordinated, and theories were proposed about its origin and composition. It seemed like 2025 would be remembered as the year of the great interstellar visitor. But the cosmos, it turned out, had another surprise in store. On September 11, 2025, Vladimir Bezegli, a Ukrainian amateur astronomer, was analyzing images from the SWAN instrument aboard the Solar and Heliospheric Observatory when he noticed something extraordinary. Hidden in the solar glare, invisible to most telescopes because of its proximity to our star, was another comet. This one was different from 3I Atlas. It wasn't an interstellar visitor, but rather a long-lost member of our own solar system family, returning after an absence of over 22,000 years. The comet, designated C2025-R2, but known as SWAN R2, had been approaching our sun for decades, hidden by the very brightness of the star it was approaching. Its discovery so close to perihelion, the point of closest approach to the sun, was almost miraculous. Just one day after Bezegli spotted it in the SWAN images, the comet reached perihelion, coming within 75 million kilometers of our star. What struck astronomers wasn't just the timing of these discoveries, but their magnificent scale. SWAN R2 sported a tail stretching across 2.5 degrees of sky, equivalent to 5 full moon diameters lined up in a row. For observers in the southern hemisphere, it became a spectacular sight through binoculars, its greenish coma and sweeping tail painting a celestial portrait against the evening twilight. As news of the second discovery spread through the astronomical community, a sense of wonder mixed with bewilderment began to emerge. What were the odds that two such significant visitors would arrive in our solar system within just months of each other? The statistical probability seemed almost impossibly small. 3IR Atlas represented only the third confirmed interstellar object ever detected passing through our solar system, while SWAN R2 was a once-in-a-lifetime visitor on an orbital period that spans most of recorded human history. Dr. Avi Loeb of Harvard University, known for his work on interstellar objects, found himself captivated by the timing. As soon as I learned about SWAN, he wrote, I was curious whether it might have originated from 3I Atlas, either as a fragment that broke off from a natural icy rock, or as a scout released by a technological mothership at a large distance. The possibility of a connection between these two cosmic wanderers seemed too intriguing to ignore. But as observations continued and orbital calculations became more precise, it became clear that these were indeed separate visitors with completely different origins. Peter Viras, Loeb's collaborator, confirmed that their arrival directions were dramatically different. SWAN originated from the direction of the Aquarius constellation, while 3I Atlas had approached from Sagittarius, toward the center of our galaxy. They were separated by tens of degrees in the sky, far too much for any realistic connection. Yet their near-simultaneous arrival continued to fascinate both scientists and the public. Here were two objects that had been traveling through space for incomprehensible periods of time, their paths determined by gravitational forces and cosmic events that occurred long before Earth had developed complex life. That they should both arrive in our brief moment of astronomical awareness seemed to speak to something deeper about the nature of cosmic coincidence. The discoveries also highlighted how much we still don't know about our cosmic neighborhood. For decades, astronomers had suspected that interstellar objects regularly pass through our solar system, but Atlas was only the third we'd ever confirmed. Meanwhile, SWAN R2 represented the category of ultra-long-period comets from the Oort cloud, that vast spherical shell of icy objects that surrounds our solar system at distances so extreme that the Sun appears as just another star. As autumn approached in 2025, both visitors continued their cosmic dance. 3I Atlas raced toward its closest approach to the Sun in late October, while SWAN R2 began its slow retreat back toward the outer darkness, not to return for more than 20,000 years. Their brief moment in our telescopes and consciousness would end, but their arrival had already begun to reshape our understanding of the dynamic, interconnected nature of our galaxy. But that's only the beginning of our story tonight. As we settle deeper into this cosmic journey, let us turn our attention to the first of these mysterious visitors, the true alien, the one that came from beyond our solar system, entirely carrying with it secrets from the deep space between stars. If you will, a journey that began before human civilization, before agriculture, before our ancestors had even learned to work metal. Somewhere in the darkness between stars, a solitary traveler began its path toward our solar system when mammoths still roamed the Earth, and our own star was just another point of light in an alien sky. This is the story of 3I Atlas, the third confirmed interstellar object ever detected, passing through our cosmic neighborhood. But unlike its predecessors, the enigmatic Oumuamua and the more conventional comet 2I Borisov, this visitor would prove to be something altogether more mysterious, more substantial, and more challenging to our understanding of what travels between the stars. The designation 3I tells its own story. The I stands for interstellar, marking it as a confirmed visitor from beyond our solar system's gravitational embrace. The 3 places it in the growing catalog of such objects. Though 3 confirmed visitors in all of human history speaks to just how rare these encounters truly are. Atlas, the survey system that first spotted it, lends its name to this cosmic wanderer, though the object itself had been moving through space long before humans existed to name anything at all. To understand 3I Atlas, we must first comprehend the almost incomprehensible nature of interstellar space. Between the stars lies a darkness so vast that light, the fastest thing in our universe, takes years to cross it. Our nearest stellar neighbor, Proxima Centauri, is 4.24 light-years away, a distance so enormous that it defies comfortable human understanding. If Earth were a marble, that star would be another marble over 6,000 kilometers away. It's in this cosmic desert that 3I Atlas spent most of its existence, drifting through the near-absolute cold and darkness of interstellar space. For tens of thousands of years, possibly much longer, it traveled through a realm where temperatures hovered just a few degrees above absolute zero, where the density of matter is so low that the best vacuum chambers on Earth seem crowded by comparison. What makes an object become interstellar in the first place? The answer lies in the violent birth and evolution of planetary systems. When stars form from collapsing clouds of gas and dust, they're often accompanied by swirling disks of material that eventually coalesce into planets, asteroids, and comets. But this process isn't gentle or perfectly organized. Gravitational interactions between forming planets can fling objects out of their birth systems entirely, sending them tumbling into the void between stars. 3I Atlas likely began its journey this way, perhaps billions of years ago, in a star system very different from our own. Some gravitational catastrophe, maybe the migration of a giant planet or the passage of another star, sent it careening out of its home system at velocities sufficient to escape that star's gravitational pull forever. From that moment, it became a wanderer, a cosmic exile drifting through the galaxy. The speed at which 3I Atlas moves tells us volumes about its origin. At approximately 60 kilometers per second, it's traveling at what astronomers call its hyperbolic excess velocity, the speed it would have in interstellar space, far from the gravitational influence of any star. This isn't just fast by human standards, it's remarkably fast even by cosmic standards. For comparison, the fastest spacecraft humans have ever built, the Parker Solar Probe, reaches peak speeds of about 200 kilometers per second, but only when diving close to our Sun and using its gravitational field for assistance. But 3I Atlas achieved its tremendous speed through natural processes, likely involving multiple gravitational encounters over its long journey through the galaxy. Each close pass by a star could alter its trajectory and speed, creating a complex orbital history that we can only guess at. By the time it reached our solar system, it was moving so fast that our Sun's gravity could barely bend its path, let alone capture it. The direction from which 3I Atlas arrived adds another layer to its mystery. It approached from the constellation Sagittarius, roughly toward the center of our Milky Way galaxy. This is significant because it suggests the object may have originated from the more crowded central regions of our galaxy, where stars are more numerous and gravitational interactions more common. The galactic center is a realm of supermassive black holes, dense star clusters, and energetic phenomena that could easily provide the kind of violent environment necessary to eject objects into interstellar space. Dr. David Jewett noted that 3I Atlas might be the oldest thing to ever pass through our solar system. This isn't hyperbole. If the object has been wandering through interstellar space for millions or even billions of years, it could indeed be older than any natural object in our solar system's current configuration. It's a time capsule from an epoch when our galaxy was younger, when different stars shone in different configurations, when the very structure of our cosmic neighborhood was arranged differently. As 3I Atlas approached our solar system, it began to reveal its secrets to our telescopes. Unlike the rocky Oumuamua, this visitor clearly showed signs of cometary activity. As it drew closer to our sun's warmth, volatile materials, primarily carbon dioxide ice, began to sublimate from its surface, creating the characteristic fuzzy coma that marks it as a comet rather than an asteroid. This cometary activity was unusual in its own right. Most comets from our own solar system do not begin showing significant activity until they're closer to the Sun than Jupiter's orbit. But 3I Atlas was already active when discovered, much farther out than typical comets begin their spectacular displays. This suggested it was rich in highly volatile materials like carbon dioxide, which vaporizes at much lower temperatures than the water ice that dominates most solar system comets. The James Webb Space Telescope's observations would later confirm this suspicion in spectacular fashion. The telescope revealed that 3I Atlas has one of the highest carbon dioxide to water ice ratios ever measured in a comet, an 8.1 ratio that was, quite literally, out of this world. This composition speaks to its exotic origin, suggesting it formed in conditions very different from those that created the comets in our own solar system. As we'll discover, this unusual composition would be just one of several anomalies that would make 3I Atlas one of the most intriguing and controversial objects ever detected. But for now, as we drift through this cosmic story, let us simply appreciate the magnitude of this visitor's journey. For 40,000 years or more, it has been approaching our solar system, crossing distances so vast that human language struggles to convey them. In the next chapter of our story, we'll turn our attention to a very different kind of visitor. One that didn't come from another star system, but from the very edge of our own, returning after a journey that began when human civilization was just taking its first tentative steps. In the mythology of many cultures, there are stories of wanderers who disappear into distant lands for decades or centuries, only to return home changed by their long journey. SWAN R2 is such a wanderer, though its journey wasn't measured in human lifetimes, but in the rise and fall of entire civilizations. While 3I Atlas arrived as a stranger from another star system, SWAN R2 came home. This comet is a native of our solar system, born in the same cosmic nursery that gave rise to our sun, our planets, and ultimately, ourselves. But its orbit is so vast, so elongated, that it spends most of its existence in the outer darkness beyond the reach of our sun's warmth in a realm where the solar system becomes indistinguishable from the void between stars. The story of SWAN R2's discovery reads like a detective novel. For months, perhaps years, it had been approaching our inner solar system, hidden by the very star it was approaching. This is a phenomenon astronomers call the Holecek effect, named after Rudolf Holecek, who first described how comets can become virtually invisible when they're positioned too close to the Sun, as seen from Earth. The comet was there, growing brighter as it approached, but our star's overwhelming brilliance rendered it invisible to ground-based telescopes. It took a special kind of telescope to find SWAN R2, one positioned in space, beyond the interference of Earth's atmosphere, and specifically designed to observe the solar wind and the space immediately around our sun. The solar wind anisotropies, SWAN instrument aboard the Solar and Heliospheric Observatory, SOHO, doesn't see invisible light like our eyes. Instead, it detects ultraviolet light at a specific wavelength emitted by hydrogen atoms, the most common element in the universe. When comets approach the Sun, the solar wind, a stream of charged particles flowing out from our star, interacts with the hydrogen in the comet's coma and tail, causing it to emit this characteristic ultraviolet glow. It's like a cosmic fingerprint that SWAN can detect, even when the comet itself is lost in the Sun's glare. On September 11, 2025, Vladimir Bazugli was analyzing SWAN images when he noticed an anomalous glow that could only mean one thing: a comet, and a bright one at that. The timing of the discovery was almost miraculous. SWAN R2 reached perihelion, its closest approach to the Sun, just one day after Bazugli spotted it. Had the discovery been delayed by even a few days, the comet might have passed through its most spectacular phase unobserved, disappearing back into the outer solar system for another 22,554 years without human eyes having witnessed its return. But what exactly is this place that SWAN R2 calls home for most of its existence? To understand this, we must journey to the very edge of our solar system, to a realm called the Oort cloud. Named after Dutch astronomer Jan Oort, who first proposed its existence, this is a vast spherical shell of icy objects that surrounds our solar system at distances so extreme they challenge imagination. The Oort cloud begins somewhere beyond the orbit of Neptune and extends outward to perhaps 50,000 to 100,000 times the distance from Earth to the Sun. At such distances, our Sun appears as nothing more than a bright star among many others. The gravitational influence of our star is so weak that these objects take tens of thousands, even hundreds of thousands of years to complete a single orbit. SWAN R2's orbital period has been calculated at approximately 22,554 years, though this number comes with significant uncertainty. Such extreme orbits are difficult to determine precisely because we can only observe comets like this for a brief portion of their journey, the small segment when they venture close enough to the Sun to become active and visible. It's like trying to determine the shape of a vast circle by examining only a tiny arc. To put this time scale in perspective, consider that SWAN R2's last visit to the inner solar system occurred around the time humans were developing agriculture and building the first permanent settlements. The Great Pyramids of Egypt wouldn't be built for another 18,000 years. Written language was still millennia in the future. Our species was just beginning to fundamentally change its relationship with the planet we call home. During SWAN R2's long absence, our Sun continued its own journey around the galaxy, carrying our entire solar system with it. Stars were born and died. The constellations shifted imperceptibly. Climate changed on Earth countless times. Ice ages came and went. And through it all, SWAN R2 was out there in the cold and dark, following its predetermined path back toward the warmth of its birth. The comet's current approach has revealed it to be a spectacular object. Its tail stretches across 2.5 degrees of sky, equivalent to about 5 full moon diameters lined up in a row. This isn't just large by astronomical standards, it's enormous. Most comets visible to the naked eye have tails measuring fractions of a degree. SWAN R2's tail is so extensive that it would be easily visible to the naked eye under dark skies, creating what astronomers describe as one of the most impressive cometary displays in recent memory. But size isn't the only remarkable thing about SWAN R2. Its composition tells a story of the outer solar system's formation 4.6 billion years ago. Objects in the Oort cloud are thought to be some of the most primitive materials in our solar system, largely unchanged since the epoch when our sun and planets were still forming from a disk of gas and dust. When we study comets like SWAN R2, we're effectively examining samples of the primordial solar nebula, the raw materials from which everything we know, including ourselves, eventually emerged. Michael Mattiazzo, an Australian comet expert who captured some of the first images of SWAN R2, described his surprise at seeing such a bright comet with a long tail when he was originally expecting to search for a small, faint patch. This speaks to the inherent unpredictability of comets, objects whose behavior can change dramatically as they approach the sun and begin to outgas volatiles that have been frozen for thousands of years. As SWAN R2 continues its journey around the sun, it's also providing astronomers with a unique opportunity. On October 5, 2025, Earth will cross through the comet's orbital path, potentially encountering debris that the comet has shed during its current visit. This could produce a meteor shower unlike any we've seen in recent memory, shooting stars that originated not from our solar system's asteroid belt, but from the very edge of interstellar space. The comet's closest approach to Earth will occur on October 19, 2025, when it will pass within 39 million kilometers of our planet, about a quarter of the distance from Earth to the Sun. For observers with binoculars or small telescopes, this will represent the best opportunity in over 20,000 years to study this particular visitor from the outer darkness. But even as we observe and study SWAN R2, we must remember that we're witnessing only a brief moment in an incredibly long story. Soon, perhaps within the next few months, the comet will begin its long journey back to the Oort cloud. Its tail will fade as it moves away from the sun's warmth. Its coma will dissipate as the frozen gases stop sublimating. And gradually, over the course of years and then decades, it will fade from view, returning to the realm of darkness where it spent the last 22 millennia. Yet, as we drift deeper into this cosmic story, we must ask ourselves, what does it mean that these two visitors, one from the space between stars, one from the edge of our own solar system, arrived in our skies at nearly the same time? Is this merely cosmic coincidence, or does their timing hint at something deeper about the interconnected nature of our galaxy? There's something almost musical about the way celestial objects move through space, a vast, silent symphony of gravitational forces playing out across distances and timescales that humble human comprehension. Tonight, as we continue our journey through the cosmos, we find ourselves contemplating one of the most intriguing questions raised by the arrivals of 3I Atlas and SWAN R2. Could there be any connection between these two wanderers? When Dr. Avi Loeb first learned of SWAN R2's discovery, his scientific curiosity was immediately piqued. Here was a prominent researcher who had spent considerable time studying interstellar objects, particularly the enigmatic Oumuamua and now 3I Atlas. The timing seemed almost too remarkable to be mere coincidence. Two significant cosmic visitors arriving within months of each other after humanity had detected only 3 confirmed interstellar objects in all of recorded history. As soon as I learned about SWAN, Loeb wrote, I was curious whether it might have originated from 3I Atlas, either as a fragment that broke off from a natural icy rock, or as a scout released by a technological mothership at a large distance. This wasn't wild speculation, but rather the kind of systematic thinking that drives scientific discovery. When faced with unusual coincidences, good scientists ask whether there might be underlying connections that aren't immediately obvious. The possibility was tantalizing. Could SWAN R2 be a piece of 3I Atlas that had broken away during some distant encounter? Comets are notoriously fragile objects, held together by little more than their own weak gravity. and the frozen ices that act as cosmic cement. Throughout astronomical history, we've witnessed spectacular comet fragmentations, like Comet Shoemaker-Levy 9, which broke apart and crashed into Jupiter in 1994, providing one of the most dramatic celestial shows ever witnessed. If 3I Atlas had fragmented during its long journey through interstellar space, perhaps due to a close encounter with another star, or from internal stresses as it warmed approaching our Sun, it's conceivable that fragments could follow slightly different trajectories. One piece might arrive as the main interstellar visitor, while another could take a more elliptical path that made it appear to be a long-period comet from our own Oort cloud. But to determine whether such a connection was possible, astronomers needed to trace back the paths of both objects through space and time. This is where the meticulous work of orbital mechanics comes into play. The mathematical detective work that allows us to determine where celestial objects have been and where they're going based on their current positions and velocities. Peter Verus, Loeb's brilliant collaborator, undertook this analysis with the precision that such questions demand. Using the most accurate observational data available for both objects, he calculated their trajectories backward through space, tracing their paths to determine their origins on the celestial sphere. The results were definitive and, in some ways, even more interesting than a connection would have been. The two visitors had arrived from dramatically different directions. 3I Atlas approached our solar system from the direction of the constellation Sagittarius, roughly toward the center of our Milky Way galaxy. This trajectory carries with it implications about the object's deep history, suggesting it may have originated from the more crowded central regions of our galaxy, where stellar interactions are more common and more violent. SWAN R2, by contrast, had approached from the direction of the constellation Aquarius. While both constellations happen to lie roughly along the ecliptic plane, the flat disk in which our planets orbit, they are separated by tens of degrees on the sky. In astronomical terms, this represents a vast difference in origin direction, far too large to be explained by any realistic fragmentation scenario. The separation between these arrival directions tells us something profound about the nature of cosmic coincidence. In a galaxy containing hundreds of billions of stars, with countless objects moving through the darkness between them, the fact that two significant visitors arrived in our small corner of space within months of each other is remarkable but not impossible. It's a reminder of just how vast and active our cosmic neighborhood really is. Consider the scale we're dealing with. Our Milky Way galaxy is approximately 100,000 light-years across and contains an estimated 200 to 400 billion stars. Most of these stars likely have their own planetary systems, many of which probably underwent the same chaotic evolutionary processes that scattered objects like 3I Atlas into interstellar space. This means our galaxy is likely filled with wandering objects, cosmic nomads drifting between the stars on journeys that span millions or billions of years. From this perspective, the near-simultaneous arrival of two significant visitors begins to seem less like an impossible coincidence and more like a natural consequence of living in a dynamic, interconnected galaxy. We're not isolated in space. We're part of a vast community of star systems that occasionally exchange materials, sometimes violently, sometimes gently, but always according to the inexorable laws of physics. The different arrival directions also tell us about the different histories these objects have experienced. 3I Atlas, approaching from toward the galactic center, may have been shaped by its journey through regions of space with higher stellar densities, more frequent gravitational encounters, and perhaps exposure to different types of radiation and cosmic phenomena. Its unusual composition, particularly that remarkable 8:1 ratio of carbon dioxide to water ice, might reflect the exotic conditions in its birth system or the experiences it encountered during its interstellar wandering. SWAN R2, traveling from our own Oort cloud, carries with it the history of our solar system's formation and evolution. Its composition should reflect the conditions that existed 4.6 billion years ago, when our Sun was still a young star surrounded by a disk of planetary building materials. In a sense, SWAN R2 is a time capsule from our own cosmic past, while 3I Atlas is an ambassador from somewhere else entirely. The gravitational choreography that brought both objects to our attention in 2025 reflects the patient, inexorable nature of celestial mechanics. Neither object decided to visit us. Their arrivals are the inevitable result of initial conditions set in motion long ago, modified by countless gravitational encounters over vast periods of time. It's a dance that began billions of years ago and will continue long after our Sun has exhausted its nuclear fuel, and our solar system has evolved into something unrecognizable. Yet there's something almost poetic about the timing of their arrivals during our brief moment of astronomical awareness. For most of human history, these visitors would have passed through our solar system unnoticed and unnamed. It's only in the last few decades that we've developed the technology and the coordinated observational networks necessary to detect and study such objects. We're witnessing this cosmic convergence at precisely the moment in our species' development when we're capable of appreciating its significance. As we drift deeper into our exploration of these cosmic visitors, we begin to understand that while they may not be connected in origin, they're connected in the profound questions they raise about our place in the universe. Each carries information about realms of space and time that we can barely imagine, and together they remind us that we live in a galaxy where the ancient past and the deep future are constantly intersecting in the present moment. But 3I Atlas, as we'll discover, holds more mysteries than just its exotic origin. As our telescopes have studied this interstellar visitor more closely, they've uncovered a series of anomalies that have some astronomers wondering whether we're dealing with something more unusual than a simple comet from another star system. In the vast silence of space, where temperature approaches absolute zero and matter is so sparse that atoms might travel for years without encountering their neighbors, something extraordinary was making its way toward our solar system. 3I Atlas carried with it not just the exotic materials of its distant birthplace, but a collection of mysteries that would challenge our understanding of what travels between the stars. As telescopes around the world and in space turned their attention to this interstellar visitor, they began to uncover a series of anomalies, characteristics so unusual that they prompted some scientists to ask whether 3I Atlas might be something more than just a natural comet. While such speculation remained highly controversial, the facts themselves were undeniable. This object was behaving in ways that seemed to push the boundaries of what we thought we knew about comets. The first anomaly became apparent when astronomers calculated 3I Atlas's trajectory with increasing precision. The object's orbit, while clearly hyperbolic and therefore interstellar, was aligned with the ecliptic plane of our solar system to within just 5 degrees. The ecliptic plane is the flat disk in which our planets orbit the Sun. A fundamental organizing principle of our solar system is architecture. For a randomly oriented interstellar object, the probability of arriving with such close alignment to our ecliptic plane is approximately 1 in 500. While not impossible, it's statistically unusual enough to raise eyebrows. Previous interstellar visitors had arrived with much more extreme inclinations. Oumuamua at 122.8 degrees and 2I Borisov at 44 degrees relative to our ecliptic plane. 3I Atlas seemed to be following a path that was almost considerate of our solar system's layout. Dr. Avi Loeb noted this alignment as one of 5 distinct anomalies that set 3I Atlas apart from typical comets. The retrograde trajectory of 3I Atlas is aligned with the ecliptic plane of the planets around the Sun to within 5 degrees, he wrote. with a chance probability of 1 in 500. For a scientist accustomed to dealing with astronomical odds, this level of improbability was worth noting. The second anomaly emerged when the Hubble Space Telescope captured the most detailed images yet obtained of 3I Atlas. The images, taken on July 21, 2025, revealed something unprecedented: a glow of scattered sunlight extending from the object toward the sun, rather than away from it, as would be expected for a typical cometary tail. Comets usually develop tails that point away from the sun, created when solar radiation pressure pushes dust and gas particles outward from the comet's nucleus. But 3I Atlas displayed a forward-facing glow that was actually longer in the direction toward the sun than it was in any other direction. This sunward extension was roughly 10 times longer than the object's width, creating an appearance unlike anything previously observed. Loeb and his colleague Eric Quito proposed an explanation involving ice fragments rather than typical dust particles. These ice fragments, they suggested, were being ejected primarily from the sun-facing side of 3I Atlas and surviving longer in the sunward direction before evaporating. But even with this explanation, the phenomenon remained unprecedented and puzzling. The third anomaly involved 3I Atlas's composition, as revealed by observations from the James Webb Space Telescope. The object displayed one of the highest ratios of carbon dioxide to water ice ever measured in a comet, an extraordinary 8.1 ratio that was, quite literally, out of this world. Most comets in our solar system have much lower ratios of these volatiles, typically closer to 1.1 or 2.1. This exotic composition suggested that 3I Atlas had formed under very different conditions from those that created comets in our solar system. It was a chemical signature from another star system, carrying information about planetary formation processes that occurred under alien conditions billions of years ago. Yet, the very richness of this composition raised questions about how such volatiles could survive a journey of tens of thousands of years through interstellar space. The fourth anomaly concerned the object's activity level relative to its size. Based on its brightness and the amount of material it was ejecting, 3I Atlas appeared to be enormous, potentially up to 20 kilometers in diameter. This would make it roughly 20 times larger than the previous interstellar visitor, 2I Borisov, and vastly larger than the enigmatic Oumuamua. The problem was statistical. Larger objects should be exponentially rarer than smaller ones in any natural population. If 3I Atlas really was 20 kilometers across, it represented a size class of interstellar object that should be extraordinarily uncommon. The fact that only the third confirmed interstellar visitor we'd detected happened to be this large struck some astronomers as improbably fortunate. However, there was uncertainty in this size estimate. If most of 3I Atlas's brightness came from the reflection of sunlight off ice fragments in its coma, rather than from its solid nucleus, the actual size of the central object could be much smaller, perhaps closer to 5 kilometers. But even this reduced size would still make it significantly larger than previous interstellar visitors. The fifth and perhaps most intriguing anomaly involved subtle changes in 3I Atlas's motion that couldn't be explained by gravitational forces alone. Like many comets, 3I Atlas appeared to be experiencing what astronomers call non-gravitational acceleration. Tiny changes in velocity that occur when material ejected from the comet's surface creates a small rocket-like thrust. For most comets, these non-gravitational forces are well understood and easily explained by the outgassing of water vapor and other volatiles as the comet heats up approaching the sun. But 3I Atlas's non-gravitational acceleration seemed to follow a pattern that was difficult to explain with standard cometary models. The timing and magnitude of these velocity changes raised questions about what exactly was causing them. Some astronomers suggested that the unusual acceleration could be explained by the object's rich carbon dioxide composition, since CO2 ice sublimates at much lower temperatures than water ice. But others wondered whether there might be more exotic explanations, perhaps involving the rotation of the object, or even more speculative possibilities. It was this collection of anomalies that led Loeb and some colleagues to explore what they called alternative hypotheses for 3I Atlas. In a series of papers and blog posts, they suggested that while the object was most likely natural in origin, its unusual characteristics warranted consideration of more exotic possibilities. Could 3I Atlas be an artificial object, perhaps a probe sent by an intelligent civilization? This suggestion proved highly controversial within the astronomical community. Critics pointed out that each individual anomaly could potentially be explained by natural processes, even if the explanations were somewhat strained. The object clearly showed cometary activity, with a fuzzy coma and evidence of outgassing. Its spectrum matched that of a body rich in carbon dioxide and water ice. There was no direct evidence of artificial construction or unnatural behavior. Dr. Tom Statler, NASA's lead scientist for solar system small bodies, summarized the mainstream view. It looks like a comet. It does comet things. It very, very strongly resembles, in just about every way, the comets that we know. It has some interesting properties that are a little bit different from our solar system comets, but it behaves like a comet. Yet, Loeb defended his speculative approach, arguing that extraordinary objects deserve extraordinary scrutiny. The most likely outcome will be that 3I Atlas is a completely natural interstellar object, probably a comet, he wrote. But the hypothesis of artificial origin is an interesting exercise in its own right and is fun to explore, irrespective of its likely validity. The debate highlighted a fundamental tension in astronomy between conservative interpretation of unusual data and the need to remain open to genuinely revolutionary discoveries. Throughout history, some of the most important astronomical breakthroughs have come from taking unusual observations seriously, even when they challenged conventional wisdom. What made the 3I Atlas controversy particularly fascinating was that it occurred in real time, as the object was still approaching the Sun, and new observations were continuously refining our understanding. Unlike Oumuamua, which was discovered only as it was leaving our solar system, 3I Atlas offered astronomers months of opportunity to study an active interstellar object in detail. As autumn 2025 approached, 3I Atlas continued its journey toward perihelion, its closest approach to the Sun, scheduled for late October. This would be the crucial test of its nature. If it behaved like previous interstellar comets, becoming more active and developing a more pronounced tail as it heated up, it would strongly support the natural comet hypothesis. If it exhibited more unusual behavior, it might keep the controversy alive. The Mars Reconnaissance Orbiter was being positioned to capture high-resolution images of 3I Atlas during its close approach to Mars in early October. These images would provide unprecedented detail about the object's structure and composition, potentially resolving some of the ongoing mysteries about its nature. Meanwhile, ground-based telescopes and space observatories continued their vigil, recording every detail of 3I Atlas's behavior as it ventured deeper into our solar system. Whatever the ultimate resolution of its anomalies, the object had already provided astronomers with the best opportunity in history to study an active interstellar visitor up close. But as we drift through this cosmic detective story, we must remember that 3I Atlas was not the only mysterious visitor gracing our skies in 2025. SWAN R2, with its own collection of remarkable properties, was simultaneously providing astronomers with a very different kind of puzzle. that of a comet from the very edge of our own solar system, carrying secrets from an epoch when human civilization was nothing more than a distant possibility. While the astronomical community was captivated by the exotic anomalies of Three-Eye Atlas, another cosmic drama was unfolding much closer to home. SWAN R2's story was one of patient return, of a wanderer that had been making its way back to the warmth of our sun for longer than recorded human history. Yet, for all its familiarity as a member of our solar system family, this comet carried its own mysteries and remarkable properties. The most striking thing about SWAN R2's discovery was how close it came to being missed entirely. For months, possibly years, the comet had been brightening as it approached the sun, but it remained hidden in our star's overwhelming glare. This celestial game of hide-and-seek, known as the Holacek effect, meant that one of the most spectacular comets in decades was invisible to the very telescopes that should have detected it earliest. Named after Rudolf Holacek, the Austrian astronomer who first systematically studied this phenomenon in the early 1900s, the effect occurs when a comet's apparent position on the sky places it too close to the sun for comfortable observation. Ground-based telescopes struggle to point in directions that would risk damage from solar radiation, while the sun's brightness drowns out all but the most brilliant objects in its vicinity. Between August 8th and September 13th, 2025, SWAN R2 was positioned within 30 degrees of the sun, as seen from Earth, close enough that most observatories couldn't safely point their instruments in its direction. During this crucial period, the comet was likely undergoing dramatic changes as solar heating began to vaporize the ices that had remained frozen for over 22 millennia. The comet was transforming from a dark, inactive chunk of ice and rock into the spectacular, tail-bearing object that would soon captivate observers worldwide. It's sobering to consider how many similar objects might have passed through our inner solar system undetected throughout history, their brief moments of glory occurring when Earth happened to be looking in the wrong direction. SWAN R2's discovery was as much a testament to the specialized capabilities of space-based observatories as it was to the persistence of amateur astronomers like Vladimir Bezugli, who spend countless hours scrutinizing astronomical images for anything unusual. The SWAN instrument that enabled the discovery represents a triumph of engineering designed for an entirely different purpose. Originally intended to study the solar wind, the stream of charged particles flowing out from our sun, SWAN detects ultraviolet light emitted by hydrogen atoms as they interact with solar radiation. When comets approach the sun, their hydrogen-rich water vapor creates exactly the kind of signal SWAN was built to detect, making it an inadvertent but highly effective comet hunter. SWAN R2's timing was extraordinary in more ways than one. The comet reached perihelion, its closest approach to the sun, on September 12, 2025, just one day after Bezugli's discovery. Had the detection been delayed by even a few days, astronomers might have missed the comet's peak activity phase entirely. Instead, they were able to witness the spectacular moment when over 20,000 years of frozen anticipation finally paid off in a burst of cometary glory. The comet's response to solar heating was everything astronomers could have hoped for. As volatiles began sublimating from its nucleus, SWAN R2 developed a magnificent tail that stretched across 2.5 degrees of sky, equivalent to about 5 full moon diameters lined up in a row. This wasn't just large by cometary standards, it was enormous. Most naked-eye comets have tails measuring fractions of a degree, making SWAN R2's display truly exceptional. Michael Mattiazzo, the Australian comet expert, who captured some of the first ground-based images of SWAN R2, described his amazement at seeing such a bright comet with a long tail when he had originally expected to search for a small, faint patch. This surprise spoke to the inherent unpredictability of comets, objects whose behavior can change dramatically and rapidly as they respond to solar heating. The comet's tail displayed the characteristic structure that astronomers have come to expect from active comets: a bluish ion tail created by electrically charged gas molecules being swept away by the solar wind, and a yellowish dust tail formed by tiny particles being pushed outward by solar radiation pressure. Yet the sheer scale of these features marked SWAN R2 as something special, a comet whose size and volatile content had been preserved through its long exile in the outer darkness. Orbital calculations for SWAN R2 revealed the truly staggering scale of its journey. With an estimated orbital period of 22,554 years, the comet's last visit to the inner solar system occurred during the late Paleolithic period, when our ancestors were still hunter-gatherers living in small nomadic groups. The agricultural revolution that would transform human civilization was still thousands of years in the future. The Great Pyramids, Stonehenge, and the first written languages all lay far ahead in time. Yet even this 22,554-year estimate comes with significant uncertainty. The Minor Planet Center's initial calculations suggested a period of around 1,400 years, with an aphelion, farthest point from the Sun, at about 250 astronomical units. Meanwhile, JPL's analysis pointed to a much longer period of 20,000 years, with an aphelion beyond 1,000 per Ordiu. The large margin of error, potentially tens of thousands of years, reflects the fundamental challenge of determining the orbit of an object that we can observe for only a tiny fraction of its journey. This uncertainty in orbital determination highlights one of the most fascinating aspects of long-period comets, like SWAN R2. We're seeing only a brief snapshot of an incredibly extended story. It's like trying to understand the plot of a novel by reading just a few paragraphs from the middle chapters. The comet's true orbital period could be anywhere from a few thousand to several 100,000 years, with profound implications for understanding its origin and future evolution. What we do know is that SWAN R2 originates from the Oort cloud, that vast spherical shell of icy objects that represents the most distant bound population of our solar system. The Oort cloud extends from perhaps 2,000 to 100,000 astronomical units from the Sun, so far away that our star appears as just another point of light among the constellations. Objects at these distances move with the patience of geological time, taking hundreds of thousands or even millions of years to complete single orbits. The Oort cloud is thought to contain trillions of icy objects, the remnants of the solar system's formation 4.6 billion years ago. These objects were originally formed much closer to the Sun, in the region where the giant planets now orbit. But gravitational interactions with Jupiter, Saturn, Uranus, and Neptune gradually scattered them outward, creating a vast reservoir of pristine materials that preserved the conditions of the early solar system. SWAN R2 is thus a time capsule from our cosmic past, carrying materials that have remained largely unchanged since the epoch when our solar system was young. The water ice, frozen gases, and organic compounds locked within its nucleus represent samples of the primordial solar nebula, the cloud of gas and dust from which our Sun, planets, and ultimately life itself emerged. As SWAN R2 continued its journey around the Sun in late 2025, it offered astronomers a unique opportunity to study these ancient materials in real time. Spectroscopic observations could reveal the exact composition of gases being released from the comet's nucleus, providing clues about the chemical conditions that existed billions of years ago. The dust particles in its tail might contain organic compounds that could shed light on the processes that eventually led to the emergence of life on Earth. But perhaps most remarkably, SWAN R2's orbit would take it across Earth's path through space on October 5, 2025. This cosmic coincidence raised the tantalizing possibility of a meteor shower unlike any seen in recent memory. Shooting stars created not by debris from our solar system's asteroid belt, but by particles from the very edge of interstellar space. Such meteor showers from long-period comets are rare and often unpredictable. The particles that create them have been locked in ice for tens of thousands of years, only recently liberated by solar heating. They carry with them the chemical signatures of the outer solar system, potentially providing ground-based observers with actual samples of materials from the Oort cloud. As we drift deeper into this cosmic story, we begin to appreciate the profound timing of SWAN R2's return. This comet began its current approach to the Sun long before human civilization existed, following a gravitational schedule set in motion by planetary interactions that occurred when our species was still millions of years from evolving. Yet it arrives at precisely the moment when we possess the technology and knowledge to appreciate its significance. But what if the paths of these two cosmic visitors, one from another star system, one from the edge of our own, had intersected somewhere in the vast darkness of space? What if, instead of arriving separately at our small corner of the galaxy, they had encountered each other in the cold void between worlds? In the infinite darkness between stars, where space and time stretch beyond human comprehension, imagine a different story unfolding. Picture, if you will, two ancient travelers on collision courses set in motion millions of years ago. 3I Atlas, the interstellar wanderer carrying secrets from another star system, and SWAN R2, the prodigal comet, returning home after over 20,000 years in exile. What if their paths had converged not in the relative warmth of our inner solar system, but in the deep cold of the outer reaches, perhaps beyond the orbit of Neptune, in that twilight realm where our sun's influence fades to nearly nothing? What if these two cosmic visitors had met in a spectacular collision that would reshape our understanding of both objects forever? Such an encounter would unfold with the inexorable patience that characterizes all cosmic events. There would be no sudden awareness, no moment of recognition between the two objects. In the vacuum of space, there is no sound, no atmosphere to carry the vibrations of impending collision. They would approach each other in perfect silence, their meeting predetermined by gravitational forces and initial conditions set in motion eons ago. The collision itself would be governed by the tremendous velocities involved. 3I Atlas, traveling at approximately 60 kilometers per second relative to our solar system, would carry kinetic energy proportional to the square of its velocity. A staggering amount of destructive force concentrated in its multi-kilometer nucleus. SWAN R2, though moving more slowly on its elongated orbit, would still possess enormous momentum from its massive size and the gravitational acceleration gained during its long fall toward the Sun. When two objects of such scale collide at cosmic velocities, the result is not simply breakage or fragmentation, but something more akin to vaporization. The kinetic energy of impact would instantly convert to heat and radiation, creating temperatures that could exceed those found in stellar cores. For a brief moment, a small star would bloom in the outer darkness of our solar system, its light taking hours to reach Earth. The physics of such high-velocity impacts are simultaneously straightforward and mind-boggling. The amount of energy released would depend on the masses and velocities of both objects, following Einstein's famous equation E=mc². If we assume 3I Atlas has a mass of roughly 10 to 12 kilograms, corresponding to a 5-kilometer diameter with typical cometary density, and SWAN R2 is perhaps 10 times more massive, their collision would release energy equivalent to hundreds of millions of nuclear weapons. But unlike terrestrial explosions, This event would occur in the vacuum of space, creating a rapidly expanding cloud of superheated gas and debris rather than a traditional explosion with a shock wave. The collision would completely destroy both original objects, reducing kilometers of ancient ice and rock to a glowing plasma that would gradually cool and condense into countless smaller fragments. The immediate aftermath would be spectacular beyond description. A debris field hundreds of kilometers across would expand outward from the collision point, containing everything from microscopic dust grains to boulder-sized chunks of shattered comet. Some of this material would retain enough velocity to escape our solar system entirely, becoming the seeds of future interstellar objects that might visit other star systems millions of years hence. Other debris would follow modified orbits around our Sun, creating a new population of objects with characteristics unlike anything currently known. Some fragments might take on highly elliptical orbits that would bring them close to Earth decades or centuries later, creating meteor showers with exotic compositions reflecting the mixed heritage of both parent objects. The collision would also create a unique chemical signature detectable across the solar system. Perhaps most intriguingly, such a collision might resolve some of the mysteries surrounding 3I Atlas. If that object truly possessed anomalous properties suggesting artificial origin, the collision would provide definitive evidence one way or another. Natural cometary materials would vaporize and disperse according to well-understood physical laws, while any hypothetical artificial components might behave differently under such extreme conditions. From Earth's perspective, the collision would initially appear as a new star, blooming in the outer solar system. Depending on the exact location and timing, it might be visible to the naked eye as a slowly brightening point of light that would gradually fade over days or weeks as the debris cloud expanded and cooled. Astronomers would scramble to point every available telescope at the phenomenon, recognizing it as a once-in-a-lifetime opportunity to study the violent destruction of cosmic objects. The scientific value of witnessing such an event would be immeasurable. Never before have astronomers observed the high-velocity collision of objects from such different origins. The data gathered could provide insights into the internal structure of both interstellar visitors and long-period comets, reveal details about the formation processes in other star systems, and test our theoretical understanding of impact physics under extreme conditions. But the collision would also represent a profound loss. Both 3I Atlas and SWAN R2 are irreplaceable archives of cosmic history. 3I Atlas carries information about the conditions in its birth star system, potentially including details about planetary formation processes that occurred billions of years ago under alien conditions. SWAN R2 preserves samples of the primordial solar nebula from which our own solar system formed, materials that have remained virtually unchanged for 4.6 billion years. Their destruction would rob us of the opportunity to study these materials in detail, to extract the chemical signatures that could tell us about the early history of our galaxy and our own cosmic neighborhood. It would be like watching a library containing the only surviving books from ancient civilizations burst into flames. Spectacular to witness, but representing an irreplaceable loss of knowledge. The debris field created by such a collision would also pose new challenges for space exploration. The cloud of fragments would gradually spread throughout the outer solar system, creating a hazard for any future spacecraft attempting to explore the outer planets or venture into interstellar space. Mission planners would need to account for this new population of debris when plotting trajectories for robotic explorers. Yet, in another sense, the collision would be profoundly creative, as well as destructive. The mixing of materials from an interstellar visitor with those from our own Oort cloud would create hybrid objects with unprecedented compositions. Some of these fragments might eventually find their way to the inner solar system, perhaps even to Earth, carrying within them the chemical signatures of both their parents. Such hybrid objects would represent a new category of solar system bodies, part local, part alien, born from the violent marriage of two ancient travelers. They would carry within their structure the story of their creation, detectable through careful analysis of their chemical and isotopic compositions. Future generations of scientists might study these collision products to understand not only the original properties of their parent objects, but also the physics of high-velocity impacts between cosmic bodies. As we contemplate this hypothetical cosmic catastrophe, we're reminded of the delicate balance that governs celestial mechanics. The fact that 3I Atlas and SWAN R2 arrived at our observatories intact, following separate paths through space, represents a remarkable coincidence of timing and trajectory. Their near-simultaneous arrival allows us to study both objects in detail, extracting maximum scientific value from these rare cosmic visitors. In reality, such collisions between major solar system objects are extremely rare events, occurring perhaps once every few million years in a typical planetary system. The vast scale of space makes chance encounters between specific objects highly improbable, despite the millions of comets and asteroids that populate our cosmic neighborhood. But as we drift back from this speculative cosmic collision to the actual story of our two visitors, we're left with appreciation for the fortune that brought them both safely to our telescopes. Their separate arrivals allow us to witness not destruction, but discovery, the opportunity to study visitors from two very different realms of our cosmic environment. Yet their timing raises its own questions about the nature of cosmic coincidence and the interconnected web of gravitational forces that governs our galaxy. As we continue our journey through this celestial story, we must ask, who are the watchers observing these cosmic visitors, and what do their arrivals tell us about the delicate balance between observation and the phenomena we seek to understand? In the grand theater of the cosmos, we find ourselves in the peculiar position of being both audience and actors, watchers and watched, as ancient visitors from the depths of space make their way through our solar system. The story of 3I Atlas and SWAN R2 is not just about these cosmic travelers themselves, but about the remarkable human enterprise of detection, observation, and understanding that has allowed us to witness their passage. Consider the vast network of eyes turned skyward that made the discovery of these objects possible. Across our planet, in remote mountaintops and desert locations chosen for their clear, dark skies, powerful telescopes stand sentinel against the night. These instruments represent the culmination of centuries of human ingenuity, from Galileo's first primitive spyglass to the sophisticated computer-controlled observatories that now scan the heavens with superhuman precision. The Asteroid Terrestrial Impact Last Alert System, ATLAS, that first detected 3I Atlas consists of 4 telescopes spread across the globe, 2 in Hawaii, 1 in Chile, and 1 in South Africa. Each night, weather permitting, these robotic sentinels methodically photograph the entire visible sky, comparing new images with previous ones to detect anything that moves or changes. It's a process that generates enormous amounts of data, hundreds of thousands of images per night, containing millions of stellar observations that must be processed and analyzed by sophisticated computer algorithms. The discovery of 3I Atlas emerged from this stream of data like a single anomalous note in a vast symphony. On July 1, 2025, the Chilean Atlas telescope detected an object moving against the stellar background at a rate that immediately marked it as unusual. But it wasn't the speed alone that caught astronomers' attention. It was the direction and trajectory that suggested something extraordinary. Within hours of the initial detection, a global network of amateur and professional astronomers had been alerted. This rapid response capability represents one of the triumphs of modern astronomy. The ability to coordinate observations across continents and time zones, bringing multiple telescopes to bear on a single target within hours of its discovery. The Minor Planet Center, the International Clearinghouse for Asteroid and Comet Observations, began collecting data from observatories around the world. The story of SWAN R2's discovery followed a different but equally remarkable path. The Solar and Heliospheric Observatory, SOHO, positioned at the L1 Lagrange point between Earth and the Sun, has been monitoring our star and its immediate environment since 1996. The SWAN instrument aboard SOHO was designed for solar physics research, intended to study the solar wind and its interaction with interstellar space. Yet it has become one of the most prolific comet discoverers in history, detecting objects that remain invisible to ground-based telescopes. Vladimir Bezygly, the Ukrainian amateur astronomer who spotted SWAN R2, represents a remarkable tradition in astronomy. The dedicated citizen scientist who contributes to professional research through careful observation and analysis. Bezygly was not using a large institutional telescope or sophisticated equipment. He was analyzing publicly available SWAN images on his home computer, searching for the subtle signatures that might indicate the presence of a comet. This democratization of astronomical discovery reflects one of the most beautiful aspects of modern space science. The same images that professional astronomers use for their research are freely available to anyone with an internet connection and the patience to learn how to interpret them. Bezygly's discovery of SWAN R2 joins a long tradition of amateur contributions to professional astronomy, reminding us that the universe is vast enough to reward all who seek to understand it. But the initial detection of these objects was only the beginning of a much more complex observational campaign. Once 3I Atlas and SWAN R2 were confirmed as significant discoveries, astronomers began what could be called the most intensive study of cosmic visitors in human history. Telescopes across the electromagnetic spectrum were pressed into service, from radio arrays that could detect molecular emissions to space-based observatories operating in the infrared and ultraviolet. The Hubble Space Telescope, humanity's most famous eye in the sky, turned its attention to 3I Atlas multiple times throughout the summer of 2025. The images it captured revealed unprecedented detail about the object's coma and the unusual forward-facing glow that puzzled astronomers. These observations required careful planning and scheduling, as Hubble's time is precious and must be allocated among thousands of competing research proposals from astronomers around the world. Even more remarkably, the James Webb Space Telescope, the most powerful space observatory ever built, devoted some of its observing time to studying 3I Atlas. Webb's incredible sensitivity and infrared capabilities allowed it to detect the exotic chemical composition that marked the object as truly alien to our solar system. The 8:1 ratio of carbon dioxide to water ice that Webb revealed was so unusual that it immediately became one of the most cited characteristics of this interstellar visitor. Perhaps most exciting was the prospect of observations from the Mars Reconnaissance Orbiter, MRO, as 3I Atlas made its close approach to the Red Planet in early October 2025. The high-rise camera aboard MRO, designed to study the Martian surface in exquisite detail, would be able to image 3I Atlas with a resolution of approximately 30 kilometers per pixel, providing the clearest view of an interstellar object's nucleus ever obtained. This represents a profound inversion of our usual perspective. For decades, we've used spacecraft to study planets, moons, and asteroids within our solar system. Now, we were using a spacecraft orbiting Mars to study a visitor from another star system. The MRO observations would essentially turn a planetary mission into an interstellar one, demonstrating the flexibility and ingenuity that characterizes the best of space exploration. The coordination required for these observations is staggering in its complexity. Astronomers must predict where fast-moving objects will be weeks or months in advance, accounting for gravitational perturbations and the object's own orbital evolution. They must compete for telescope time, justify their observing proposals, and coordinate with colleagues around the world to ensure comprehensive coverage. But there's something almost poetic about this global effort to study cosmic visitors. Here are objects that have traveled for tens of thousands or millions of years through the emptiness between stars, only to encounter a small blue planet whose inhabitants have just recently developed the ability to detect and study them. It's as if the universe has arranged a cosmic appointment, bringing together ancient travelers and curious observers at just the right moment in the development of human technology. The observations themselves reveal as much about us as they do about the objects we're studying. Every spectrum, every image, every measurement represents a question we've learned to ask about the universe. The chemical composition that Webb detected in 3I Atlas is remarkable, not just because it's exotic, but because we've developed the theoretical understanding and instrumental capability to recognize its significance. Similarly, the unusual orbital alignment and forward-facing glow that characterize 3I Atlas are anomalies only because we have sufficient experience with comets to recognize when something doesn't fit the usual patterns. We're witnessing these objects through the lens of accumulated human knowledge, seeing them in the context of everything we've learned about planetary formation, stellar evolution, and the physics of small bodies in space. Yet for all our sophisticated instruments and theoretical understanding, there remains something humbling about these cosmic encounters. 3I Atlas and SWAN R2 existed long before Earth developed complex life, and they'll continue their journeys long after our civilization has become a footnote in cosmic history. We're privileged to witness their passage during our brief moment of astronomical awareness. The observations also remind us of our responsibilities as cosmic observers. We may be the only intelligent beings in our local region of the galaxy capable of studying and appreciating these visitors. If there are no other technological civilizations within hundreds of light years of Earth, then we represent the universe's only chance to understand what 3I Atlas and SWAN R2 can teach us about stellar formation, planetary evolution, and the nature of interstellar space. This responsibility extends beyond mere scientific curiosity. The data we gather from these observations will become part of humanity's permanent record of the cosmos. Information that future generations will build upon as they develop even more sophisticated ways of studying the universe. Every spectrum, every orbital measurement, every chemical analysis becomes part of the growing archive of human knowledge about our cosmic environment. As we drift deeper into the stories these visitors carry, we begin to appreciate the profound messages locked within their ancient materials, chemical signatures that speak to us across time about the birth of solar systems, the evolution of our galaxy, and the patient processes that shape the cosmos on scales we're only beginning to comprehend. There is something profoundly moving about holding a meteorite in your hands, knowing that this small piece of rock and metal has traveled through space for millions or billions of years before finding its way to Earth. But the cosmic visitors of 2025 offer us something even more extraordinary: the opportunity to study, in real time, materials that carry messages from the deepest reaches of time and space. 3I Atlas and SWAN R2 are not just astronomical curiosities, they are libraries written in the language of chemistry and physics. Their compositions encoding stories that span the history of our galaxy. Each molecule, each isotopic ratio, Each grain of dust tells us something about conditions that existed in places and times we can barely imagine. Consider first the tale that 3I Atlas brings from its journey between the stars. This object formed around another star, in a planetary system that may have been dramatically different from our own. The building blocks of that distant solar system were forged in the nuclear furnaces of stars that lived and died before our sun was even born. The carbon, oxygen, silicon, and other elements that make up 3I Atlas were created through stellar nucleosynthesis, the process by which stars transform hydrogen and helium into heavier elements through nuclear fusion. When the James Webb Space Telescope revealed 3I Atlas's extraordinary 8:1 ratio of carbon dioxide to water ice, it was reading a chemical signature that had been written billions of years ago. This composition tells us that the comet formed in a region where carbon dioxide ice was particularly abundant, relative to water ice conditions that are rare in our own solar system, but might be common around other types of stars. The prevalence of carbon dioxide suggests that 3I Atlas formed in the outer regions of its birth system, where temperatures were cold enough for CO2 to freeze, but where the protoplanetary disk was rich in carbon-bearing compounds. This might indicate a star system with a different chemical composition than our own, perhaps one that formed from a molecular cloud enriched in carbon by previous generations of massive stars. Dr. Jacqueline McCleary of Northeastern University noted that this composition offers a potential glimpse into the conditions that exist in other solar systems and how those systems formed in the first place. It's as if 3I Atlas is a geological sample from an alien world, carrying within its structure information about planetary formation processes that occurred under completely different conditions from those that shaped our own cosmic neighborhood. But the messages from 3I Atlas go deeper than just its bulk composition. The very fact that it has survived its journey through interstellar space tells us about the conditions in the galaxy between stars. For tens of thousands of years, this object has been exposed to cosmic radiation, interstellar dust, and the tenuous but corrosive environment of the interstellar medium. The survival of delicate organic compounds and volatile ices during such a journey provides constraints on the density and temperature of interstellar space along 3I Atlas's path. If the object had encountered regions of higher density or temperature, its composition would have been altered. The preservation of its exotic ice ratios suggests that the space between stars, at least along certain paths, is even emptier and colder than we had previously understood. The object's trajectory also carries information encoded in its orbital elements. 3I Atlas approached from the direction of Sagittarius, toward the center of our galaxy, where stellar densities are higher and gravitational interactions more frequent. This suggests that interstellar objects might be more common than we previously thought, constantly being ejected from the central regions of the galaxy and wandering outward through the spiral arms. The speed at which 3I Atlas travels, approximately 60 kilometers per second, provides clues about the violence of its ejection from its home system. Such high velocities typically result from close encounters with massive objects, perhaps during the migration of giant planets or the passage of another star through its birth system. The comet carries within its motion the memory of some ancient gravitational catastrophe that sent it tumbling into the cosmic void. SWAN R2 tells a very different but equally profound story. As a denizen of our own Oort cloud, this comet is a time capsule from the earliest days of our solar system. The materials locked within its nucleus have remained largely unchanged since the epoch 4.6 billion years ago, when our sun was still a young star surrounded by a disk of planetary building materials. The water ice, organic compounds, and rocky particles that make up SWAN R2 were present in the primordial solar nebula. the cloud of gas and dust from which everything in our solar system eventually condensed. When we study this comet's composition, we are essentially examining samples of the raw materials from which Earth, the other planets, and ultimately life itself emerged. The comet's 22,000-year orbital period carries its own message about the early dynamics of our solar system. SWAN R2 was likely formed much closer to the Sun, in the region where the giant planets now orbit. But gravitational interactions with Jupiter, Saturn, Uranus, and Neptune gradually scattered such objects outward, creating the Oort cloud as a vast repository of pristine materials from the solar system's youth. This scattering process was not gentle or gradual. Computer simulations suggest that the early solar system was a chaotic environment where planetary orbits were still evolving and gravitational encounters could dramatically alter the trajectories of smaller objects. SWAN R2 is a survivor of this cosmic reshuffling, flung outward during the solar system's adolescent phase and preserved in the deep freeze of the outer Oort cloud. The comet's current return allows us to study materials that formed under the same conditions that gave rise to Earth's oceans and atmosphere. The water molecules in SWAN R2's nucleus might be chemically identical to those in our planet's hydrosphere, carrying the same isotopic signatures that reveal the cosmic sources of Earth's water. Some of those molecules might even have contributed to Earth's early oceans during the late heavy bombardment, when comets and asteroids were still frequently impacting the inner planets. The organic compounds that spectroscopic observations might detect in SWAN R2's coma represent another profound message from deep time. These carbon-based molecules formed in the cold outer regions of the early solar system, where complex chemistry could occur without being disrupted by intense solar radiation. Some of these compounds might be precursors to the biochemical molecules that eventually enabled life to emerge on Earth. When we analyze the dust and gas streaming from SWAN R2's nucleus, we're witnessing the release of materials that have been locked in ice for longer than complex life has existed on our planet. These substances were frozen when Earth was still a molten ball of rock, retry NA continue edit, when the moon was much closer and the days were only a few hours long. They carry within their molecular structure the chemical signature of a solar system that existed before continents, before oceans, before the first stirrings of life in some primordial tide pool. The timing of SWAN R2's return adds another layer to its message. This comet began its current approach to the Sun long before human civilization existed, following a gravitational schedule set in motion when our species was still millions of years from evolving. Yet it arrives at precisely the moment when we possess the technology and knowledge to appreciate its significance. There's something almost orchestral about this timing, as if the universe has arranged for us to witness these cosmic visitors at the exact moment in our development when we can understand what they represent. Had SWAN R2 arrived a century earlier, we would have seen it as little more than a bright, fuzzy star. Had it arrived a century later, we might be so focused on interstellar exploration that a mere Oort cloud comet would seem mundane. But arriving now in 2025, SWAN R2 provides us with a perfect complement to the exotic 3I Atlas. Together, these visitors offer us a comparative study of cosmic materials, one carrying the chemical signatures of an alien star system, the other preserving samples from our own solar system's birth. It's as if the universe has provided us with both a control sample and an experimental specimen for understanding planetary formation processes. The spectroscopic analysis of both objects reveals isotopic ratios that carry their own profound messages. Isotopes are versions of the same element with different numbers of neutrons in their nuclei. The relative abundances of different isotopes depend on the nuclear processes that created them. Stellar nucleosynthesis, supernova explosions, cosmic ray interactions, and other phenomena that occurred over billions of years of galactic evolution. When astronomers measure the ratio of heavy water, deuterium oxide, to normal water in these comets, they're reading a record of the conditions in the molecular clouds from which their parent star systems formed. The deuterium to hydrogen ratio is particularly sensitive to temperature and density during the early stages of planetary system formation, providing a cosmic thermometer that records conditions billions of years ago. Similarly, the ratios of different carbon, nitrogen, and oxygen isotopes in both comets carry information about the stellar sources of these elements. Massive stars produce different isotopic signatures than smaller stars, and supernova explosions create their own distinctive patterns. By comparing the isotopic compositions of 3I Atlas and SWAN R2, astronomers can begin to understand the different stellar environments that contributed materials to each object. These isotopic measurements also allow us to test our theories about galactic chemical evolution. Our galaxy has been gradually enriching itself with heavy elements over billions of years as successive generations of stars have lived, died, and scattered their nuclear products into space. The compositions of 3I Atlas and SWAN R2 represent samples from different epochs and locations in this ongoing process. The organic compounds that both comets likely contain carry perhaps the most intriguing messages of all. These carbon-based molecules form through complex chemistry in the cold environments of stellar nurseries and planetary system formation regions. Some of them are the same types of compounds that serve as the building blocks of life: amino acids, sugars, nucleic acid bases, and other biochemically important molecules. The detection of such compounds in 3I Atlas would tell us that the chemistry of life is not unique to our solar system. If amino acids or other prebiotic molecules formed naturally around the alien star that gave birth to this interstellar visitor, it would suggest that the chemical foundations of biology are universal features of planetary system formation. SWAN R2's organic content provides a different but equally important perspective. These molecules would represent the chemical inventory that was available when life first emerged on Earth. Some of the organic compounds in this comet might be identical to those that rained down on our planet during the late heavy bombardment, potentially contributing to the chemical soup from which the first living organisms emerged. But beyond their scientific value, these cosmic visitors carry a more philosophical message about our place in the universe. 3I Atlas reminds us that we are part of a galaxy filled with other star systems, some of which have produced materials that eventually find their way to our cosmic doorstep. We are not isolated in space, but connected through the vast processes that govern stellar birth, planetary formation, and the ejection of materials into interstellar space. SWAN R2 tells us a different but complementary story about cosmic connectivity. This comet links us to our own deep past, carrying materials that participated in the formation of our solar system and potentially contributed to the emergence of life on Earth. It reminds us that we are made of star stuff in the most literal sense. Atoms forged in stellar cores and assembled into complex molecules in the cold depths of space. Together, these visitors illustrate the deep time perspective that astronomy brings to human consciousness. We exist for mere decades in a universe that operates on timescales of billions of years. The materials that make up our bodies, our planet, and these cosmic visitors have been cycling through the galaxy for eons, participating in countless cycles of stellar birth and death, planetary formation and destruction. As we contemplate the messages encoded in these ancient travelers, we begin to understand that astronomy is not just about studying distant objects, but about reading the history of the universe itself. Every photon that reaches our telescopes, every spectrum we analyze, every chemical signature we detect is a message from deep time, carrying information about processes and events that shaped the cosmos long before Earth existed. Yet these messages also point toward the future. The organic compounds, water ice, and rocky materials that make up 3I Atlas and SWAN R2 will continue their cosmic journeys long after their brief passages through our solar system. Some fragments might eventually be incorporated into new planetary systems, perhaps contributing to the emergence of life around other stars. The carbon atoms that currently form complex molecules in these comets might someday become part of alien biochemistry billions of years in the future. As our two cosmic visitors continue their respective journeys toward the outer darkness, we're left to contemplate the profound messages they've delivered. But their departures also raise deeper questions about the nature of cosmic time and the ephemeral moment we represent in the vast history of the universe. There is a profound melancholy in astronomical farewell. Unlike earthly departures, when cosmic visitors leave our neighborhood, they carry with them the weight of deep time. The knowledge that their return, if it comes at all, will be measured not in years or decades, but in millennia or eons that span the rise and fall of entire civilizations. As autumn deepened in 2025, both 3I Atlas and SWAN R2 began their slow retreat from the inner solar system, their brief moments of glory fading as they moved away from the sun's warmth. For astronomers around the world, this departure marked not just the end of an extraordinary observational campaign, but a poignant reminder of the cosmic scales on which the universe operates. 3I Atlas, having completed its closest approach to the Sun on October 30th, 2025, began accelerating back toward interstellar space. The gravitational assist it received from our star would add to its already tremendous velocity, ensuring that it would eventually leave our solar system even faster than it arrived. Unlike the comets that belong to our solar system family, this visitor would not be returning. Its trajectory was hyperbolic, an open curve that would carry it away from our sun forever. The object's departure offered astronomers their final opportunities to study an active interstellar visitor up close. As 3I Atlas moved away from the sun, its cometary activity gradually diminished. The carbon dioxide and water ice that had been sublimating from its surface began to freeze again, and the spectacular coma that had made it visible to our telescopes slowly faded. Within months, it would return to being just another dark object drifting through space, indistinguishable from the cosmic background except for its remarkable velocity. By early 2026, 3I Atlas would cross the orbit of Jupiter, still accelerating under the sun's gravitational influence. By 2027, it would pass beyond Saturn, entering the realm of the outer planets, where sunlight becomes so faint that solar heating becomes negligible. The exotic ices that had created its unusual cometary display would return to their frozen state, locked away until the object might encounter another star millions of years in the future. The final observations of 3I Atlas came from the most distant spacecraft in our solar system, Voyager 1 and Voyager 2, the twin probes that have been journeying outward since 1977. Though these ancient explorers lacked the sophisticated instruments needed for detailed study, they could potentially detect the object's passage as it headed toward the interstellar medium. It would be a fitting farewell, one interstellar traveler acknowledging another as they passed in the cosmic night. SWAN R2's departure followed a very different timeline, but carried its own sense of cosmic finality. Having reached perihelion on September 12, 2025, the comet began its long journey back to the Oort cloud, following the same gravitational path that had brought it inward over the previous decades. But while its outbound journey would retrace its inbound path, the comet itself had been fundamentally changed by its encounter with the sun. The solar heating that created SWAN R2's magnificent tail had also depleted some of its volatile materials. Each time a long-period comet makes such a journey, it loses a portion of its mass to space. Water vapor, carbon dioxide, methane, and other ices sublime away, never to return. The rocky and dusty materials left behind gradually accumulate on the comet's surface, creating an insulating layer that affects how it will behave during any future encounters with the Sun. For SWAN R2, this process of change and evolution will continue throughout its outbound journey. As it moves beyond the orbit of Mars, then Jupiter, then the outer planets, the comet will gradually return to its dormant state. The tail that once stretched across degrees of sky will dissipate. The coma that made it visible to amateur astronomers will fade. Within a year or two, SWAN R2 will become invisible to all but the most powerful telescopes, a faint speck of reflected sunlight gradually disappearing into the outer darkness. The comet's journey back to the Oort cloud will take centuries. By the time it reaches the halfway point of its orbit, around the year 2500, human civilization will have evolved in ways we cannot imagine. The telescopes that observed SWAN R2's 2025 apparition will be museum pieces, replaced by instruments and technologies that exist only in the realm of speculation today. Yet SWAN R2 will continue outward, following the inexorable gravitational schedule that governs its 22,854-year orbit. By the year 3000, it will have moved beyond the influence of the outer planets, entering the realm where our Sun's gravity is barely stronger than that of nearby stars. The Earth that it glimpsed during its brief passage through the inner solar system will have completed more than 1,000 orbits around the Sun, while the comet will still be climbing outward toward its distant aphelion. It's sobering to contemplate the future that awaits our world during SWAN R2's next complete orbit. When this comet returns to the inner solar system around the year 47,579, humanity will have had more time to evolve than has elapsed since our species first emerged in Africa. The very continents will have shifted perceptibly under the influence of plate tectonics. New mountain ranges will have risen while others eroded away. Ice ages will have come and gone dozens of times. The stars themselves will have moved in their eternal dance around the galactic center. Constellations that seem permanent to us will have changed their shapes as stellar proper motions accumulate over tens of thousands of years. The bright stars that guided ancient navigators will have evolved, some growing dimmer as they age, others exploding as supernovae, and disappearing entirely from the night sky. Yet SWAN R2 will remember our solar system as it was in 2025. The gravitational relationships between the planets, the Sun's steady nuclear burning, the basic architecture of our cosmic neighborhood, these will remain essentially unchanged when the comet returns. It will carry within its nucleus the same water ice that reflected sunlight during its 2025 apparition, the same organic compounds that formed 4.6 billion years ago in the primordial solar nebula. The departure of both cosmic visitors also marks the end of what many astronomers consider to be the most intensive study of interstellar and long-period objects in human history. The coordinated observations of 3I Atlas involved telescopes on every continent and spacecraft throughout the solar system. The James Webb Space Telescope, Hubble, the Mars Reconnaissance Orbiter, and countless ground-based instruments all contributed to our understanding of this interstellar visitor. Similarly, SWAN R2 mobilized amateur astronomers around the world, creating a global network of observers who tracked the comet's evolution as it moved through the inner solar system. The images captured by dedicated astrophotographers like Michael Mattiazzo became part of humanity's permanent record of this remarkable visitor from the outer reaches of our solar system. But perhaps the most profound aspect of these cosmic farewells is what they teach us about the nature of time itself. In our daily lives, we measure time in minutes, hours, days, and years, scales that reflect the rhythm of human existence. But the universe operates on vastly different timescales, where million-year journeys are brief episodes and billion-year processes are the norm. 3I Atlas has been traveling through space since before our solar system formed its current configuration. It will continue its journey long after our sun has evolved into a red giant and consumed the inner planets. From the perspective of cosmic time, the few months it spent within range of our telescopes represents an infinitesimally brief moment. A cosmic eye blink during which two civilizations, one ancient and wandering, one young and curious, happen to cross paths. SWAN R2's story operates on slightly more comprehensible but still staggering timescales. Its orbital period spans most of recorded human history, linking the present moment to epochs when our ancestors were just beginning to develop agriculture and build permanent settlements. When it returns, our species will have had as much time to evolve as separates us from the emergence of modern humans. These departures also remind us of our responsibility as cosmic observers. We may be the only technological civilization within hundreds of light years capable of studying and appreciating these visitors. The data we gathered during their passages through our solar system becomes part of humanity's permanent archive of cosmic knowledge, information that future generations will build upon as they develop even more sophisticated ways of understanding the universe. The spectra we captured, the images we recorded, the orbital measurements we made, all of these become part of the scientific legacy we leave to our descendants. When future astronomers detect similar interstellar visitors or long-period comets, they'll compare their observations with the detailed records we made of 3I Atlas and SWAN R2. Our moment of contact with these cosmic travelers becomes a reference point for understanding the broader population of objects that wander through our galaxy. As both visitors fade from view, disappearing into the cosmic background from which they emerged, we're left with more than just scientific data. We're left with a profound sense of connection to the larger universe, an awareness that we live in a galaxy where ancient materials circulate endlessly between stars, where objects older than our planet occasionally grace our skies, where the chemistry of distant star systems can be studied in our own cosmic backyard. The silence that follows their departure is not empty, but full of possibility. Somewhere in the darkness beyond our solar system, other ancient travelers are making their way toward us, carrying within their structure the stories of distant places and times. The Vera Rubin Observatory, now beginning its systematic survey of the southern sky, will likely detect many more such visitors in the coming decades. Future interstellar objects will be compared against the benchmark set by 3I Atlas, just as future long-period comets will be measured against the spectacular display of SWAN R2. The discoveries of 2025 have established a new baseline for understanding these rare but profound cosmic encounters. But for now, as we drift toward the end of this cosmic story, we can only marvel at the fortune that brought these two ancient wanderers to our attention during our brief moment of astronomical awareness. In the vast history of the universe, the few months when 3I Atlas and SWAN R2 graced our skies represent an almost impossibly brief convergence of circumstance and capability. We witnessed visitors from realms we can barely imagine, one from the space between stars, one from the edge of our own solar system. During the only period in human history when we possessed the technology and knowledge to appreciate their significance. It's a reminder that we live in a universe far stranger and more wonderful than our ancestors could have imagined, where ancient travelers occasionally emerge from the darkness to share their secrets with anyone curious enough to listen. As both visitors return to the cosmic night from which they came, they carry with them not just the materials of their birth, but the memory of a small blue planet whose inhabitants paused in their daily concerns to witness their passage. In the vast loneliness of space, perhaps that moment of recognition, one ancient wanderer acknowledging another across the gulf of deep time, represents something precious and rare in the cosmic story. Subscribe to join our community of stargazers as we continue exploring the wonders that unfold in the darkness above us each night.